Imagine a client that needs one business outcome, but reaching that outcome means calling several objects in the right order. The facade pattern gives that client a clear, task-shaped entrance to the larger system. It is a structural pattern. It changes how the client reaches existing capabilities without changing what those capabilities fundamentally do. The facade accepts a request, coordinates the necessary collaborators, and returns a useful result. It does not need to hide every subsystem, and it does not forbid advanced clients from using those subsystems directly. Its purpose is narrower and more practical, make the common path easy to understand and hard to misuse. A useful facade has a few recognizable characteristics. First, it speaks in the client's language. A method such as submit an order is more useful at the boundary than a sequence of low-level setup calls. Second, it delegates real work instead of re-implementing every subsystem. Third, it owns coordination, ordering, early exits, and the final result belong in one visible place. Finally, it creates a stable boundary around details that may change independently. A facade is not automatically a singleton, a service locator, or the owner of every dependency. Those are separate design choices. The essential idea is a simpler interface placed in front of a more involved collaboration. There are 3 participant roles. The client asks for an outcome and should know as little coordination detail as possible. The facade exposes the smaller public surface and translates that request into an ordered collaboration. The subsystems perform the specialized work. They do not need a reference back to the facade, so they remain usable on their own. Dependency direction matters. The client depends on the facade, and the facade depends on the subsystem abstractions or objects it coordinates. One system can also have more than one facade, each shaped around a different audience. That keeps the boundary focused instead of turning one class into a catalog of unrelated operations. Facade is a good fit when callers repeatedly reproduce the same multi-step workflow, when a library needs a friendly entry point, or when an application layer should protect clients from infrastructure details. It can also isolate a third-party integration behind language that belongs to your domain. Do not add it merely because a subsystem has several classes. If the direct API is already small and clear, another layer adds ceremony. It is also a poor fit when each caller genuinely needs different low-level control. Watch for 2 failure modes: a facade that grows into a God object, and a convenient method that conceals important cost, failure, or security behavior. Keep the operation cohesive, return honest outcomes, and leave specialized access available when the domain requires it. Our example is a community fabrication lab. Submitting one laser cutting job requires 4 kinds of work: inspect the request, reserve its material, start ventilation, and place the job in the laser queue. Each responsibility is valid on its own, but the ordinary client must currently know the order and every early exit. We will first build that direct version so the design pressure is visible. Fabrication request will carry the input and result. Fabrication subsystems will contain the 4 specialists. Program will act as the client. Only after the baseline runs will we create FabricationDesk as the facade. That keeps the implementation tied to the participant map we just established. We begin in an empty file with the data that crosses the boundary. As fabrication request is typed, its name states the operation's input rather than exposing any subsystem. Member ID identifies the caller, material names the requested sheet, and estimated minutes gives the specialists the small piece of scheduling information they need. Submission result is equally deliberate. Accepted answers the decision, while message preserves a reason the client can display. These records contain no coordination logic. That separation will let the direct client and the facade use exactly the same contract, so our later comparison changes structure rather than behavior. Now we create the first specialist in a second empty file. When Design Inspector appears, the name tells us this class answers one question: is the submitted design acceptable? Its inspect method receives the request and checks only the rules it owns. A missing member ID fails immediately. An estimate outside 1 to 120 minutes also fails. Otherwise, the design is approved. Notice what is absent: The inspector does not reserve inventory, start equipment, or queue a job. That narrow responsibility matters because the facade should coordinate capable objects, not absorb all of their work. We stay in the same file, move below the inspector, and add the next specialist. As material inventory appears, the class name keeps the responsibility concrete. The private sheets dictionary is a tiny in-memory stock ledger for this example. Try reserve communicates that a reservation can fail without using an exception for an expected outcome. Inside that method, quantity is the current number of sheets. If the material is unknown or quantity is 0, the method returns false. Otherwise, it subtracts 1 and returns true. The inventory still knows nothing about design rules, ventilation, or the laser queue. The last two specialists model machine operations. Ventilation system exposes start for because the workflow needs ventilation for a known number of minutes. Then laser cutter appears as the object that owns queue numbering. The private next job number stays inside that subsystem. In queue, job ID names the stable value we return to the caller, while the console line makes the proof visible later. These classes are deliberately small, but they are not fake facade methods. Each one owns behavior the coordinator should request in sequence. We move the cursor to the new lower section instead of leaving part of the code below the visible area. With the specialists ready, we switch to the empty client file and type the direct workflow. The variable design inspector appears first, followed by material inventory, ventilation system, and laser cutter. These names are clear, but their presence is already evidence that the client knows every participant. The request is inspected, and inspection names that first decision. Result must then be assigned through 3 branches: reject an invalid design, reject unavailable material, or start ventilation and queue the job. Job ID belongs to the success branch, and status converts the final result into terminal-friendly text. This code works. The issue is not correctness. It is where the coordination knowledge lives. Before changing the design, we run the baseline. The terminal shows ventilation being reserved, a job receiving its identifier, and the final accepted result. That proof matters because a refactoring needs a behavioral reference point. We now know the 4 specialists cooperate correctly and that the direct client produces the outcome we expect. Nothing about the next step should change this successful path. We are changing who knows the sequence. Return to program and read it as a dependency map. The client constructs 4 specialists, knows inspection must happen first, knows material must be reserved before the machines start, and knows how to assemble the success result. If a second client submits jobs, that sequence can be copied in Drift. Now move to the Subsystem tab. Each class is focused and reusable. None of them is the natural owner of the entire use case. Back in Program, the branching block is the pressure point. The common workflow needs a home of its own between this client and these specialists. We open the final empty teaching file and create the boundary. As FabricationDesk appears, the name is intentionally domain-facing. A client at this lab understands a desk that accepts a job. It should not need a class named Subsystem Coordinator. Because this project is pinned to .NET 10 and C#14, the 4 collaborators go directly into the class declaration as a primary constructor. Every dependency stays explicit without 4 fields and 4 assignment lines. The parameters remain available throughout the class, and nothing creates hidden global state. At this point, the class owns no workflow yet. We have only established the facade participant and its dependency direction. Now the facade receives its task-shaped operation. As submit is typed, the method name describes the client's goal, not the mechanism. Inspection stores the first subsystem result because an invalid request should return immediately. The next branch asks inventory to reserve the requested material and turns failure into the same result contract. Only after both gates pass do we start ventilation and queue the request. Job ID names the successful queue outcome, and the final result carries it back across the boundary. The code is familiar because we are moving proven coordination, not inventing new business rules. The cursor follows the method to keep its lower lines visible. Switch back to Program and separate 2 roles that share this small file. Create Fabrication Desk is the composition route. Something must assemble the four collaborators, and that wiring is allowed to know their concrete types. Run Client is the client from our pattern diagram, and its only dependency is FabricationDesk. As FabricationDesk is typed, the name tells the reader where submissions go. We create one accepted request and one rejected request, so the next run covers both a successful queue and an unavailable material. Each call is now submit, followed by print. Run Client no longer knows inspection order, reservation rules, ventilation timing, or job identifier construction. Run the application again. The first request reserves ventilation, receives job 001, and returns accepted. The second request asks for steel, which inventory does not contain, so it returns rejected before ventilation or queuing runs again. The terminal gives us both sides of the comparison. The successful behavior survived the structural change, and the early exit behavior is now consistent behind one operation. Program became smaller without making the subsystem work disappear. That is the facade pattern doing its actual job. The result is simpler, but the trade-offs remain real. FabricationDesk now depends on 4 collaborators and owns their ordering, so changes to this use case converge there. That is helpful while Submit stays cohesive. If unrelated reporting, maintenance, billing, and administration operations accumulate in the same class, the facade becomes a bottleneck. The direct subsystem APIs also still matter for tools that need specialized control. Finally, a convenient method must not hide important failure or cost. Our result reports rejection, and the method's name describes a real business action. Use the facade to clarify a boundary, not to pretend complexity no longer exists. Here is the pattern in one pass. A client needs one outcome. Several focused subsystems provide the real capabilities. The facade exposes a smaller, domain-shaped operation and owns the common coordination sequence. We first proved the direct workflow, then moved that sequence into FabricationDesk without moving the specialist behavior. Program now calls submit and receives an honest result. Reach for facade when repeated orchestration is the problem. Leave the direct path alone when it is already clear or when callers truly need different low-level control. A good facade does not erase complexity. It gives that complexity a deliberate entrance.